important application of Newton's 3 laws. And to get started, I'm just going to put this block on the board, and I'm going to give it a little push. And what happens? So I give it a push, it accelerates, according to Newton's second law, and then it starts to slow down. But that violates Newton's first law, right, which is that an object in motion stays in motion unless there's an external force. So there must be another force acting on it. Any guesses what that might be? That's right, it's friction. Now friction's really important. It helps us walk. It's actually important for the invention of the wheel, for the utility of the wheel. So it's important that we try to understand it. And as scientists, what we often try to do is we build models to try to understand something and then evaluate whether they work or not. So let's try that. We're going to build a model for friction. So one common idea is that friction is due to the fact that all surfaces have little tiny grooves in them. And when the grooves from this block interact with the grooves on this piece of wood, those rough surfaces start to push against each other, right? So let's start with that as a working assumption. Now, another component to our model is that friction is a force, right? So all forces have two very vital components, which is a direction and a magnitude, and we can try to figure out what those might be from a couple of experiments. So we can actually infer the direction just from that simple experiment we did a moment ago. I give it a little push, it accelerates, moves, and then slows down, right? So the frictional force is pushing away from the direction of motion. So we actually can see from Newton's second law, if it's decelerating, the acceleration vector is opposed to the velocity vector, so that means the force is opposing the motion. So we'll say opposes motion or applied force. Now for the magnitude, let's try another experiment. What I'm going to do is put the block at the top of the board, and I'm going to start to lift it up a little bit. And you can see that the block remains stationary until the incline gets so high that the force due to gravity pulls the block down. So we can draw a free body diagram for this. And what we have is we have our inclined plane with an angle theta. We have a block, which is on that piece of wood. We have what forces? There's the force due to gravity, that's right, pointed vertically downward, mg. We have a normal force pointed out. And then which way does the frictional force point according to our model? That's right, it's pointed up this block, right? So we'll call that F sub F. And it's pointed away from the direction of motion. Now, one thing we do know about the magnitude is that right before the block starts to slide, the frictional force is reaching sort of a maximum value, right? Because as we lift the incline up, the weight is pulling down more in the x component if we define x to be along the piece of wood and y perpendicular to it. And so we can try to estimate what the maximum value of that frictional force might be. So let's break this up into x and y components. We know that this angle right here is theta, and you can do a homework problem to prove that. Let's first write the y component of the vectors. There's the normal force is entirely in the y direction, and then there's the y component of the weight, which is going to be mg times the cosine of theta. And then the frictional force, F sub F max, is equal to mg times the sine of theta. Now we can solve for mg is equal to n divided can plug this into equation 2, and we can get F sub F max, the maximum value of the frictional force, is equal to N times sine of theta divided by cos theta. And I've actually already measured this wood block, and it's 29.5 inches long. And I even measured the height at which it starts to slide, and that's 8.5 inches. And so we can calculate this to be about 0.3 times n. So this is really revolutionary, right? So we have a working model which shows that the maximum value of the frictional force depends on the normal force, right? And we can even extend this a little bit and say, make a working assumption that the frictional force is equal to some coefficient mu times the magnitude of the normal force. Now, this turns out to be a pretty good approximation, but not quite accurate. And let's do a little thought experiment. Have you ever pushed something heavy like a refrigerator across the floor? What happens when you do that is you push a little bit, and then the refrigerator doesn't move. You push a little harder, it still doesn't move. You push even harder, and then it gives way and it starts to move. And what's happening there is there's a transition between what's called static friction, which corresponds to stationary objects, and kinetic friction, which corresponds to sliding objects, things that are already moving in motion. And the difference there, going back to our model, is that if you have these grooves, when you're pushing on something, and it pushes back on you, just like Newton's third law, you're actually sort of pushing those grooves in closer together. You're getting them closer together. The intermolecular forces are working, and it gets harder and harder to break that bond. So it actually gets a little bit easier once you make that transition into kinetic friction. And we can envision this with a graph where we have the applied force on the x-axis and the frictional force on the y-axis, right? So I push a little bit. Newton's third law says it pushes back on me with the same force. I push a little bit more, same force pointed back at me. I push even more, and I reach a maximum value. It starts to give way. And this maximum value actually turns out to be equal to the magnitude is some constant, mu sub s, which is a coefficient of static friction, which you can look up, times n. And then for kinetic friction, this is actually pretty cool. It's actually a constant. So F sub F is equal to mu sub k times n. And it's always lower, mu sub k, the coefficient of kinetic friction, is always lower than the coefficient of static friction, exactly because of our model. So this is up to mu sub n, and it's going to be mu sub s times n or mu sub k times n. Now I want to end with one more demonstration, which is, watch what happens when I take this block and I put it against the board and I hold it there. What's happening here? So I'm pushing directly into the block, so I'm pushing into the board. The normal force is pointed which way? It's pointed out of the board, right? The weight is pulling it downward, and where's the frictional force? The frictional force is actually the thing that's holding it up, which is really cool. So the frictional force is pointed upward. It's opposing the motion to fall down. And if I'm pushing really hard right now, and the board's pushing back on me really hard, and if I let go a little